Hello, this is a continuation lecture of time response of second order system. In the time response of second order system, we have seen the zeta and omega n are a very key role in the second order system. These are called behavioral characteristics of a second order system. Zeta and omega n. Zeta and omega n are behavioral characteristics of second order system. Second order system. Okay, so now I'll touch upon the zeta. When the zeta varies, okay, what is the change in the output? What is the behavioral change in the output? That's called what is the change in the response? What is the change in the, is the response is oscillating? Is the response is not oscillating? Is the response is oscillating and then coming to the steady state? So this is a very important aspect, especially this lecture. How the poles, already we have seen the poles, zeros and characteristic equation also, zeros, poles, and before that I'll talk about S plane, zeros, poles and characteristic equation. For example, to find poles, zeros and characteristic equation, we are familiar with the transfer function, closed loop transfer function and open loop transfer function. Suppose for example that is C of S divided by R of S equal to 10 into bracket S plus 2 and S into bracket S plus 4 and S plus 6. Suppose this is the closed loop transfer function of a one system. It may be electrical system, it may be mechanical system, it may be electromechanical system, or it may be chemical system. So I got a mathematical modeling of a one system. From this transfer function, this is called closed loop transfer function. From this transfer function, I will find the poles, zeros and characteristic equation. So suppose for example, if I make denominator equal to 0, then S into bracket S plus 4 plus S plus 6 is equal to 0. Here the highest power of S is 3, so that we will get a 3 poles. Roots, it's exactly in the mathematics is called roots, but in the control system it is called a poles. Sometimes it may be S plus 2, 4 means 4 poles, sometimes S plus 2 means 2 poles. Now here I will write S1 is equal to 0, S2 is equal to minus 4 and S3 is equal to what? Minus 6. These are the poles of a above transfer function. What exactly happened? If you put any one value of a pole in the above transfer function, that transfer function becomes what? Infinity. The transfer function becomes infinity. Now poles are 0, minus 4 and minus 6. The poles. Okay. Now this is a way to find the poles. Now this is case 1. Now I will go for case 2. In the case 2, I will make numerator equal to 0. Here 10 into bracket S plus 2. 10 is called a gain. Here only one 0, that is only one root. S is equal to minus 2. This is called what? 0. 0 equal to minus 2. Why it is called 0? If you put this value in the above transfer function, the transfer function becomes 0. If you put the above 0 in the transfer function, this becomes 0, so that the minus 2 value is called 0. And case 3, what is the case 3? The case 3 is nothing but denominator equal to 0, that is S into bracket S plus 4 plus S plus 6 is equal to 0, S into bracket 10S plus 24 equal to 0, S cube plus 10S square plus 24S is equal to 0. What is this? This is called a characteristic equation. This is called characteristic equation. The highest power of characteristic equation is 3 here, sometimes 4, sometimes 5, depends upon the transfer function. So quickly we came to know that how to find the poles and how to find the zeros from the above transfer function. This is a method to find the poles and zeros and characteristic equation from any given transfer function. I hope you understood how to find the poles and zeros. Okay. Now I'll show on the S-plane. First of all, I'll explain what is meant by S-plane. I'll explain what is meant by S-plane. So S-plane is very common in the control system. Even you draw a root locus, you draw a polar plot, you draw a Nyquist plot, you need a S-plane. Even in a Rao's stability criterion, you need a S-plane. The S-plane is nothing but there are two axes, the vertical axis and one is the horizontal axis. Horizontal axis is real axis, vertical axis is what? Complex axis. S is equal to j omega, complex. And this is called what? S-plane. Now I locate the poles. What are the poles now? I'll write here. Zeros are 0 is equal to what? -2, and poles are what? 0, -4 and -6. The into sign for poles, the into sign, and for zeros, small circle without field. So that first I'll locate all the poles. 0, into sign, -4 and -6. This is a way to locate the poles on the S-plane. Now the remaining is 0, -2, small circle without field, okay, without field, that is -2. This is a 0 and these 3 are poles. This is a way to locate on S-plane. Okay, so now we will move to the zeta. If I change the value of zeta and how there is a drastic change in the output of any system. Okay. So now the question is a response of the system versus zeta. Now I keep omega n remains constant. Suppose if it is a mechanical system, omega n equal to root of k by m. K is the stiffness of the system, m is the mass of the system. Now I will put omega n is a constant, only I change the zeta. Zeta means c, I am changing. You know the formula for zeta and c, 2 zeta omega n m. Okay, and how to calculate the c and all, you know. Okay, suppose this is the oil above and below, and this is a clearance, and definitely this is a d, and this is a h. Okay, and this is a capital D is the diameter. So and viscosity, c is a function of mean viscosity and clearance and diameter and h. Okay, fine. Once we calculate the c, we can calculate the zeta. Now in first case of zeta, in my case, the zeta is what? This is called what? Underdamping. When the zeta is greater than 0 and less than 1, it is called underdamping. In the last class, I have given the classification. So when the underdamping, I find the poles. My main objective is to response versus zeta. So response depends on the poles. So now we know the standard form of second order transfer function. Closed loop transfer function of second order system is equal to omega n square divided by s square plus 2 zeta omega ns plus omega n square. Now I will take denominator equal to 0. Now s square plus 2 zeta omega ns plus omega n square is equal to 0. Now I'll find S1 comma 2 is equal to minus B plus or minus square root of B square minus 4 AC. Here A is 1 and C is omega n square divided by 2A. So S1 comma 2 is equal to minus zeta omega n plus or minus square root of, it goes inside the root 4 zeta square omega n square minus omega n square. Now S1 comma 2 is equal to minus zeta omega n plus or minus omega n root of zeta square minus 1. Okay. So now you see here, zeta is less than 1 already I have written, so that you put any value 0.1, 0.2, 0.3, 0.99 under the root is negative. How to make it in a positive way? So plus or minus omega n, I will take minus 1 is a common, then 1 minus zeta square. 1 minus zeta square is now positive. Okay. Now what is the minus 1? Minus 1 is a j square or I square. So but j square or I square is equal to what? Minus 1. So S1 comma 2 is equal to minus zeta omega n plus or minus j square and 1 minus zeta square. Okay, I'll take j is outside the bracket, then omega n root of 1 minus zeta square. Correct? Now I know what is the omega n root of, but I know omega d equal to damped natural frequency is equal to natural frequency root of 1 minus zeta square. Therefore S1 comma 2 is equal to minus zeta omega n plus or minus omega dz. So S1 is minus zeta omega n plus omega dz and S2 is minus zeta omega n minus dz. Now what are the nature of poles? S1 and S2 are the poles. What are the nature of poles? Now poles are what? Now poles are negative real with complex. Now poles are negative real with complex. For example, suppose you take zeta is 0.5, omega n is 10, then you will get minus 5 plus. So something, omega is 10, something 8j something. So now poles are negative real with complex. So I can show on S plane. Okay, this is S is equal to j omega and sigma minus zeta omega n, and here this is called omega d. So that S1 is minus zeta omega n plus omega dj and S2 is minus zeta omega n minus omega dj. Okay, so what happens if the poles are, this is very important, what is the inference of this graph? When the poles are negative real with complex, due to complexity, what happened? You will get a sine function in the response. Response is C of t. Okay. Now I'll write due to complex part 3j minus 3j, for example. Due to complex part in the poles, there is sine function in the response equation. Response means output equation. Whenever there is a sine function, definitely what happens? The system is oscillating. Due to sine function, the system is what? Oscillating or vibrating. When in the case of underdamping, definitely the system is vibrating. Now we'll see the response equation in the next lecture, but tentatively the output means if you take a spring mass system, you pull this spring mass system up to here, then leave it here. Zeta is what? My zeta is what? This is C of t is nothing but x of t. This is x of t. So if you pull it and leave it, so it starts for oscillating, it will come to rest. Definitely there is oscillation because due to complex part in the poles, there is a sine function in the response. We'll see in the sine function C of t. This is called response equation. Next class we will derive what is the C of t for underdamping. We come to know. Next is case 2. Next is case 2 for critically damping. Now case 2, it is called critically damping. In the critically damping, zeta is equal to what? 1. We know the standard form of closed loop second order transfer function. And poles, how to get a poles? Denominator equal to 0, that is s squared plus 2 zeta omega ns plus omega n square is equal to 0. You put zeta equal to 1 because it is a critical damping. S squared plus 2 omega ns plus omega n square is equal to 0. Once again you will get two roots, s plus omega n whole square, that is s plus omega n equal to 0, s plus omega n is equal to 0. Now s1 is equal to minus omega n, s2 is minus omega n. Now what are the nature of poles? Now the nature of poles are what? Negative real with repeated. Negative real with repeated. In the previous case, negative real with complex, when zeta is less than 1, exactly when zeta is equal to 1, the poles are what? The poles are negative real with repeated. Means what? No complex part. First point, no complex part in the poles, so that no sine function in the response, so that no sine function in the response means what? No oscillation in the response, no oscillation. These are the three inference when the system is critically damping. So I can show here the same spring mass system I'll take, but C is equal to what? Zeta is equal to what? 1. Okay, viscosity of the oil I have increased. If I pull this mass below by certain amount and leave it, it goes slowly. And stops. It is not crossing the mean position. This is C of t. This is what? The initial position. Now it is no oscillation because there is no any complex part in the poles. Negative real with repeated, so that when the zeta changes, nature of poles are changes. When the nature of poles are changes, in the response curve it changes, in the output behavior of the system changes. Okay. Now we'll see the case number 3. Okay. In case number 3, that is called when zeta is greater than 1 and less than infinity. This is called what? Overdamping. The case is called overdamping. We know the standard form of transfer function of second order system. Okay. Denominator equal to 0, I'll get a poles. S square zeta omega n s plus omega n square is equal to 0. Here I'll find s1 comma 2 minus b plus or minus square root of b square minus 4ac divided by 2a. Now s1 comma 2 is equal to, if I divide this, it goes under the root, it becomes 4 zeta square omega n square minus omega n square. Now I'll take omega n square common, then outside the root is omega n zeta square minus 1. Here zeta is greater than 1, so that under root is always positive. Okay, s1 is equal to minus zeta omega n plus omega n root of zeta square minus 1, and s2 is minus zeta omega n minus omega n zeta square minus 1. You can take example, for example, zeta is 2 and omega n is 10. Definitely we'll get s1 and s2 in numerical values. Now I'll locate on the s plane. Now I'll locate on the s plane. So both are negative, means this is the s2 is here and s1 is here. Now what is the nature of poles now? Now nature of poles are what? Negative real with unrepeated. Now poles are negative real with unrepeated. Negative real with unrepeated. Negative real with unrepeated. So no complex part once again. No complex part in the poles. Hence no sine function. Hence no sine function or oscillation in the response. Here also the body is not vibrating. Here also the body is not vibrating. Now I'll show the response curve. Now in this case, the response curve becomes, in this case I'll take a spring mass system with a high viscosity of oil, that C will be greater, and automatically what happened, the zeta will be greater. I'll pull this mass up to here and leave it, so it reaches to the mean position. It will take more time when zeta is greater than 1 and less than, zeta is equal to greater than 1 and less than equal. Here already I have drawn here, this is called zeta is equal to 1. Compared to this is a more sluggish. So this is x of t, because the output of this system is displacement, and this is the t time. Okay, we will come to know how the system will be sluggish when the zeta decreases. The last case, the case number 4, is called very ideal case, that is zeta is equal to 0, no damping. It is called undamping. The last case, case number 4, undamping. Undamping means what? Zeta is equal to 0, no damping. It's like in the vacuum. The vacuum, if the spring mass system is vibrating in the vacuum, so what is the closed loop transfer function? And when denominator is equal to 0, then here you put zeta is equal to 0, s square is equal to omega n square is equal to 0, s square is equal to minus omega n square, and what is the minus? Minus 1 is equal to j square and y square. S1 is j omega n, S2 is what? minus j omega n. Now poles are what? You can see the poles on S plane. So one is S1, second is S2. The value is omega n j and minus omega n j. So here the first inference is what? The poles are pure complex. Poles are pure complex. Due to pure complex, what happened? There is a sine function in the output. There is sine function in the output. Hence, there is a sustained oscillation in the output. Okay, so we can see the graph here. The output, this is the constant frequency. It starts for oscillating x of t. It starts for oscillating. For example, the oscillation of spring with no damper, only spring and mass, especially in the vacuum. So just you pull the mass by some amount m, it starts for oscillating. So in the vacuum, so no damper, zeta is 0. This is the response. So quickly we came to know that all four cases, case 1, case 2 and case 3, when the zeta changes, so definitely the nature of pole changes. When the nature of pole changes, then what happened? There is a change in the behavior. So if I draw the graph, combined graph, when zeta is equal to 0, what is the value of S1 and S2? That is omega n. When you increases the zeta, say 0.1, 0.2, 0.3, it starts for moving like this, and exactly when zeta is equal to 1, and this value is also omega n. This is omega nj and omega minus plus omega nj minus omega nj. Here omega minus omega n minus omega. When zeta is what? Greater than 1. When zeta is greater than 1. And here when zeta is greater than 0 and less than 1. This is the movement of poles by changing the zeta. Here when zeta is here, zeta is 0.1, 0.2, 0.3, 0.4, exactly 1, 1.2, 1.3, 2, 3, 4 like this. This is the how the poles are moving by changing the value of zeta. Okay. So I'll summarize, finally I'll summarize in a one table. Finally, so the serial number 1, 2, 3, 4, 4 cases, and zeta in this case is less than 1, in this case equal to 1, in this case greater than 1 and less than infinity. Here zeta is equal to 0. And type of damping, it is called type is called under damping and critically damping and over damping and undamping, and S1 and S2. In this case, S1 is minus zeta omega n plus omega dj. Here minus zeta omega n minus omega dj. And critically damping minus omega n minus omega. And over damping minus zeta omega n plus omega n root of zeta square minus 1 minus zeta omega n minus omega n zeta square minus 1. In this case, omega n j minus omega n j. S1 and S2. Otherwise, I can write in this case, oscillating. In this case, system is oscillating, not oscillating, and not oscillating. In this case, oscillating with sustained frequency. Oscillating with sustained frequency. It's the entire the output. The entire summary I have covered in one page. Okay, these are basics of how the zeta changes with respect to how the poles are changing with respect to zeta and the system behavior. Next class we will see the time response of second order system under unit step input. Thank you.